Hi everyone! In the last lessons we have seen how to define the denotational and operational semantics of a simple language with arithmetic expressions. Now we are going to do the same, but in a language of statements, which includes, among other things, assignments, conditional statements, and loops. In this video we are going to start with the definition of big step semantics and some of its properties.
Let's start by recalling the syntax of the language we are dealing with. We denote by STM the set of statements which is generated by the grammar you see here below. The skip statement does absolutely nothing, it's just a placeholder. We'll have statements, which means that the result of evaluating E is going to be stored in the variable X. The semicolon here represents a sequence of a statement. That means first execute S1 and then execute S2. We also have the classical conditional statement, the if then else, and we also have while loops. Our while loops just executes the statement inside repeatedly as long as the condition B remains true. So assume that we want to give semantics to the execution of a statement. We assume that we have an initial state that gives the values of the variables before executing the program. Unlike expressions, statements don't return anything, but they change the state. So the result of executing a statement is a final state, what we call sigma prime. So for example, assume that we have this statement here, and which is a sequence of two statements, and the initial state that maps y to the integer 2 and the other variables to 0. So we want to define our semantics in such a way that after the execution of this statement, we get the following state sigma prime, in which y remains as is, but x and z obtain their corresponding values. So we're going to define a relation that relates statements, initial states, and final states. And the notation you see here means that if we execute s and the initial state is sigma, we obtain sigma prime as a final state. In the same way as we did with the language of arithmetic expressions, we are going to define this relation by means of axioms and rules. So let's start with the rules. As always, we distinguish cases. In the case of a skip, this statement does nothing. So if we execute a skip and the initial state is sigma, then the final state will be the same sigma, because we are not doing anything and we are not changing anything. This is what the axiom skip BS says. So now we move on to variable assignment. If we want to execute such an assignment from a given state sigma, what we have to do first is evaluate the expression under that state. And we have already the denotational semantics for these expressions, which is A of E under the state sigma. This is the value of the expression. So the assignment replaces the existing value of x in sigma by the result of evaluating the expressions under that sigma. By using the notation we have seen before, this is what we get. A state that behaves exactly like sigma except in the variable x. Let's see this rule with an example. Assume that we have this statement, so we assign the result of x times 5 to the variable y, and assume that the initial state is the one that mapped x to the number 2 and y to the number -1. So first we evaluate the expression under the given state, which means that we get a sigma of x times 5, which is in this case 10. So after executing this statement, we get the same state, but now y contains the value 10. The next case we are going to deal with is the case of a sequence of two statements. What happens if we want, for example, to execute S1 followed by S2 under a state sigma? Well, we first execute S1 under that sigma and we obtain another state, sigma prime. Now we are going to execute S2, but in the same state that was left by S1 after its execution. So we obtain as a result sigma second, which is also the state resulting from executing the whole sequence. So if we have derivations for the two statements and the final state of the first derivation coincides with the starting state of the second derivation, then we can find a derivation for the whole sequence. So let's see this with an example. Assume that we want to execute x equals 3 followed by y equals x times 2. So our initial state maps every variable to 0, for example. So first we execute x is assigned the value 3 by using the rule for assignments. So at the end in our state x has the value 3. Then we execute the second assignment using the state we have before. So if we use the same rule for the semantics, for the assignments, we realize that the semantics of x times 2 is 6, and the result of the state, the result is the state that maps x to 3 and y to 6, which is in turn the result of the whole sequence. Now we move on to conditions. If we want to evaluate an if-then else statement, we have to evaluate the condition first. So we have the semantics for that. We have b of b under the state sigma, which can be true or it can be false. So let's assume first that the condition is true under that state. So in this case we execute S1, which is the statement in the then branch of the conditional under the same state sigma. So we obtain sigma prime as a result, which is the final state of the whole conditional. Analogously, we will have another rule that covers the case in which the semantics of b is false. So in this case we will execute S2, which is the statement of the else branch of the conditional. And here I show an example. If I want to execute the statement that you see here, and the initial state is, for example, y contains the value 2, then we evaluate the condition, which is true under that state. So we have to apply the first of the rules we have seen in the conditional, which is if t. So now we execute the body of the then branch, which is that thing here, under the state we have seen earlier. So now we have a sequence of statements for which we use the sec rule we have seen earlier. So those are the derivation of both components of the sequence. In both cases we use the rules for assignments. So this is the rule assign that we are using here and also here, and this is the rule sec that we are using here. So after the two assignments we have here that x maps to 3, y maps to 1, which is the state of the whole sequence, and so is the state of the whole conditional. Last but not least, let's study the rules for while loops. The first thing we got to do is to evaluate the condition again. So the first case that we are going to deal with is the case in which the condition is false. So in this case we don't enter the loop, and the results therefore is the same state as the one we started with. Now if the condition of the while loop evaluates to true, we do enter the loop. So we have to execute first the body of the loop, which is S under the state sigma. And let us assume that we find a derivation such that the final state is sigma prime. Then we have to try to execute the loop under that same state sigma prime, that is, after we have executed the body of the loop. This means that now we will take the condition B again, but now under the state sigma prime, and depending on the result we will use here the rule while t or while f. Regardless of this, at the end of this derivation we will obtain a state sigma second, which is the final state of the outer derivation as well. I think we can understand this better with an example. So assume that we want to execute this loop under a state in which y contains the value 2. So first we evaluate the condition. Y different from 0 under the state y map to 2. So in this case this condition is true. So we have to apply the while t rule. This means that we have to execute the body of the loop under that state, and we obtain this state y equals 1. And then we try to execute the loop again under this state we have earlier. So now we are going to evaluate the condition again. The condition is true again, so here we apply also the while t rule, and which means that we have to execute the body of the loop. We obtain y mapped to 0, and then the loop again. And now if you look here, the condition of the loop is false under this state. So we have to apply here while f. So the condition doesn't hold. The final state is the same as the state we have before. And this state that we also have here, and is also the state that we have here. So at the end, after executing the loop, y is mapped to the value 0. Okay, now that we have seen all the rules, let's study some of the properties. The first one we are going to see is determinism. It's very similar to its counterpart in the language of arithmetic expressions. So if we start from a statement and an initial state sigma, and we obtain sigma prime on the one hand, but on the other hand we have also another derivation with the same statement, the same initial state, but a sigma second as a final state, then the proposition says that both final states must be equal. In other words, if we fix the statement and the initial state, if there exists a final state, then that final state is unique. I mean, there's only one final state. The next thing we are going to see is not a property, but rather a definition, which is the equivalence between statements. We say that two statements are equivalent if they have the same behavior for every input state. That is, if we obtain sigma prime as a result with the first statement, then we also obtain the same sigma prime as a result with the second statement s prime, and also the other way around. An application of equivalence is the following one. So if we have two nested sequences, such as these ones, it doesn't matter how we nest them. So whether we nest them like this, in this case, so we will have something like semicolon and S3, and in the right hand side we have another semicolon with S1 and S2, or whether it's nested like this, we have S1 here, here a semicolon, S2, S3. Well, both things are semantically equivalent, and this can be proved by using the definition we have seen before and the rules of sequence. The proof of this is one of the exercises that you can find in the Campus Virtual, so I leave it to you as an exercise. Another important thing with the semantics is that we cannot always find a final state. That is, there are some statements and some initial state such that we cannot find a derivation such as this one. An example of this is the statement while true do skip. So if we execute this under any state sigma, no matter what it is, actually, we say that the condition is going to be true. So here we're going to apply the rule while t, which means we have to execute the body of the loop, which is a skip, under the state sigma, and the skip rule says that we have the same sigma. And now we have to execute the loop again under the sigma that was here before. So we have here sigma again, and okay, so here we will apply in here the rule while t again, and we have the same problem. We have the same sigma, the condition is true, and we have the derivation for skip. We have another derivation for the while true to skip, in which we will have to apply again the rule while true, and so on. So at the end we have the same problem with the same condition, and there's no finite derivation for this program. And derivations here are like mathematical proofs. They have to be finite. So in conclusion, if a computation is not terminated, then this is reflected in our semantics as the impossibility of obtaining a derivation tree.